Right now, as you're watching this video, time is moving faster for you than it is for the person orbiting Earth on the International Space Station. Astronauts who spend 6 months in orbit come home a tiny fraction of a second younger than they would have been if they'd stayed on the ground. Today we're going to figure out why, and by the end, you'll understand why GPS on your phone would be broken by miles if we ignored this. The speed of light in a vacuum is the same for every observer, no matter how fast they're moving. It's one of the strangest facts in physics. Think about it this way. If you're driving 60 miles per hour and you throw a ball forward at 10 miles per hour, someone standing still sees that ball moving at 70 miles per hour. Speeds add up, but light doesn't play by that rule. If you're in a spaceship moving at half the speed of light and you shine a flashlight forward, someone standing still doesn't see the light moving at 1.5 times the speed of light. They see it moving at exactly the speed of light, same as you do. So if speed equals distance divided by time, and the speed of light has to stay constant for everyone, something else has to give. That something is time itself. Let's make this concrete with a thought experiment Einstein basically used himself. A light clock. Picture a clock that ticks every time a photon bounces between two mirrors. One on the floor, one on the ceiling of a spaceship. Bounce up, bounce down. That's one tick. Now put that ship in motion, flying past you at high speed. From your point of view, standing still outside the ship, the photon isn't just going straight up and down anymore. It's also moving sideways with the ship. So the path it traces is a diagonal zigzag. And a diagonal path is longer than a straight vertical one. Since the speed of light can't change and the distance just got longer, the time for one tick has to get longer too. That's time dilation. To you, watching from outside, the clock on the moving ship is ticking slower than your own clock. Not because anything is wrong with it, because time itself is passing more slowly for it, relative to you. It's not that clocks are physically affected by speed, it's that time itself slows down. Every process, your heartbeat, your metabolism, radioactive decay, the burning of a candle, all of it slows down together in exactly the same proportion. That's why there's no way to feel time dilation from the inside. If you're the one moving, your brain, your wristwatch and the light bouncing in your eyeballs are all slowing down at the same rate. Everything still looks completely normal to you. This leads to the most famous thought experiment in relativity, the twin paradox. Say you have twins. One stays on Earth. The other boards a rocket, accelerates to near light speed, flies to a distant star, turns around and comes back. When the traveling twin returns, they're younger than the twin who stayed home. The paradox part comes from a tempting but wrong idea. Couldn't the traveling twin just as easily say they stayed still and the Earth twin moved away and came back? Wouldn't each see the other as younger? The resolution is that the situation isn't actually symmetric. The traveling twin has to accelerate, to speed up, turn around and slow down. The Earthbound twin never does. That break in motion is what makes the traveling twin the one who genuinely experiences less time. Acceleration breaks the symmetry. Now you might be thinking, fine, the math checks out, but has anyone actually seen this happen? Yes, repeatedly. Muons are unstable particles created when cosmic rays hit our upper atmosphere. They decay so fast that, without time dilation, almost none of them should survive the trip down to sea level. But because they're moving at close to the speed of light, time dilation lets far more of them survive the trip than classical physics would predict. We detect them by the billions. And then there's GPS. Satellites orbit fast enough that their clocks run slightly slow from time dilation. But they're also far enough from Earth's gravity that general relativity speeds their clocks back up by an even larger amount.
Net effect: satellite clocks gain about 38 microseconds a day compared to clocks on the ground. That sounds tiny. But GPS calculates your location using the time it takes signals to travel at the speed of light. A 38 microsecond error compounds into a positioning error of about 10 kilometers a day if it isn't corrected for. Quick bonus, because I mentioned it. Speed isn't the only thing that dilates time. Gravity does too. This is general relativity's contribution. Clocks run slower the deeper they sit in a gravitational field. A clock at sea level ticks very slightly slower than a clock at the top of a mountain. Near a black hole, the effect becomes extreme. Time can slow to a crawl relative to a distant observer as you approach the event horizon. Einstein didn't just say time is relative as a poetic idea. He showed exactly how much and why. And we've confirmed it with particles, with satellites, and with atomic clocks flown on airplanes. Like and subscribe if you want more of this, and I'll see you in the next one.